Hey everyone, today we are doing another LeetCode 75 problem, number 162, find peak element. A peak element is an element that's strictly greater than its neighbors. Given a zero-indexed integer array nums, find a peak element and return its index. The array contains multiple peaks, return the index of any of the peaks. Also, we can assume that nums of -1 and nums of n, so immediate values outside of the array are both negative infinity, so they're automatically the lowest possible value. So if we only had one element, for instance, let me write this out. If we only had a 1, for instance, this would technically be negative infinity. That'd be negative infinity. This would be our peak. The whole caveat of this problem, and the whole reason why it's a medium and it's not a one-liner easy solution, is because they want us to solve it in O of log n time. And in LeetCode 75, this comes under a binary search problem. So we have to use some kind of binary search algorithm to effectively solve this in log n steps. If you guys don't remember what a binary search is, you are basically reducing your size, the size you're searching, by half with every iteration. It works great on a sorted array. If your array is sorted, then, and if you have a number that you want to find that's greater than the midpoint, you could completely eliminate the bottom half. The caveat with this problem, once again, is that it's not necessarily sorted. Let's go through this problem because I feel like it has a few clever tricks to solve it, and it may not seem obvious at first. For starters, base case, if we have just one element, return that element as the peak. In fact, if we have two elements, we can return the greater of the two as the peak. And if we have no elements, if it's an empty array, actually no, it has to be at least one. So we can eliminate that case. Now, what do we do when we have more than two elements, which are unsorted, right? We have to use some kind of binary search. Let's take the second example. 1, 2, 1, 3, 5, 6, 4. In this case, we can either return 2, that's a valid max, because these values are both smaller, or we can return 6, because these immediate values are both smaller. Like, this is the global maximum, right? The global max. But we don't necessarily have to return the global max. We just have to return a max, a peak. So I say if we start with binary search approach and start in the middle, we compare it with its immediate right neighbor. If it's greater than, so in this case we have 5 greater than 3, I think we can confidently say that our value will lie somewhere in the right hand side. And that's because, what other clues do we have? Is that necessarily true? I could have 3, 5, 6, 7. Okay. So if we know this value is greater, right? We could definitely say this side has a max. And that is because in the case that there's any number less than 5 here, and since there's a 4, this is automatically a max. And in the case where this number is greater than, right? So this won't be a max, but this could potentially be a max. And then our next iteration, we can jump to that number and make that the new middle. And if this isn't the max either, right? In this case, this wouldn't be the max. In the next iteration, we jump there. And similar to a binary search, we're always cutting our sample size or our working list by half, and we effectively have a O of log n solution. Now, in the other case where this number is less than our middle number, for the sake of simplicity, let's just make this 2 for now. Let's proceed with this side, right? And let's have the 3 included. because we can't eliminate 3 because there's a chance that could be the max too, right? The reason we eliminated 3 when we're searching the right-hand side is because we knew the 5 was strictly greater than the 3, so the 3 had no chance of being a max. But in the left-hand case, it is possible that 3 could still be the max. And in this case, we once again search. We go to 2 as our new midpoint. And we check that. Check if its right is greater. If it's not, then we go. When does our thing end? We start with 2 pointers, one on that end and one on that end. We define our mid, and if our mid is greater than our mid plus 1, we make the new J pointer to be here, and then we continue to iterate, making 4/2 I plus j, 3/2, 1.5, making this the new mid. Yeah. And we keep repeating this. So that becomes the new mid. And the right is still less than, so the J pointer. This would now become the new J pointer. 2, 0. This would be our new mid. And in our new mid, we know the right is greater than. So the I pointer would move there. And officially, we keep doing this until I is no longer less than j. So once I is officially equal to j, we exit out of the loop, and we just return whatever I is, which in this case is pointing to 2. Alright, sweet. Let's type the solution up. I'm sorry if that was more complicated than it should be. I would say what is one of the more clever solutions for solving this problem in log n time. We say if len of nums less than or equal to 1, return. Wait, if len of nums equals to 1, return nums 0. Could set I to be 0, j to be len nums minus 1. And now we could say while I less than j, mid equals I plus j over 2 if mid greater than, mid greater than nums of mid. So we're saying if the left-hand side is where we think the max is, our j would just equal our mid. And no 2 adjacent numbers could be equal. That's one of the things that they mention in our constraints. I equals mid. Again, we just want to return I. Let's run this and see what it says. I feel like something caused a runtime error. I just don't know what. Parentheses here. Yeah, I realized something was off, but hopefully that should fix all my errors. But 1 expect 0. Why does it expect 0 here? Oh, it's the index. It's not the number itself. So I could just return 0. Nice. Great, thank you guys for watching. If this was a useful LeetCode solution for you guys, please do like, comment, and subscribe for more content. And I will catch you guys next time. Peace.